Hamaus, research fellow at the Ludwig-Maximilian University in Munich, Germany. He obtained a PhD in 2012 in Zurich under the supervision of Uro, then Uro Seider, sorry, Uro Seider. Then he moved to States, in Illinois and in France, particularly spent first postdoc in IAP in Paris, then he's back to Germany in where he's actually working. He's an expert in cosmology. He's working on the statistics of large-scale structure, and in particular, he's one of the major experts in the world about cosmic voids. In fact, he's responsible of the activity inside Euclid about the voids, the cosmological exploitation of cosmic voids, and in fact, the today talk will be devoted to cosmology with cosmic voids. Thank you to be here. Okay.
Thank you, Lauro. Thank you, everyone. It's amazing to be here. It's my first time in Bologna in the astrophysics department, or anyway at the university, because I only know Bologna from my free time before, but I was already a fan. So it's great to be here also professionally now. And of course, I'm going to talk about cosmic voids, no surprise. This has been going on for a while, but now we're mostly focused, of course, on the near future, which is Euclid. So this is going to be a bit more focused on that part, and really, the short-term future of that research that we can do with actual data. So let me see, does this work? Okay, just to set the tone as a teaser, I mean, I don't have to explain much about this here to you, but of course, cosmology is exciting in exciting times. We have tangents coming up, whether they're real or fake, so to be seen. We have these kind of two separate class of tangents. You can see them maybe in the growth of fluctuations, or the level of the perturbations, not of the background, but also of the background expansion. So we have maybe 2, maybe 3 sigma disagreements between lensing and clustering measurements, and also C and B. And then there's even more, maybe 5, maybe more sigma in H naught. So certainly something interesting. We don't know what it is, but it looks severe. If you look at, for example, this plot, it shows you very clearly that lambda CDM currently is not able to reproduce these data points. It's mostly driven by the redshift 0 supernova constraints, this tangent, or the Cepheids. But we certainly need to figure out what's going on. So that's basically the teaser. And now, where do the voids come in? We need something. I think we need to look from a different angle. We need something else to check this, right? Maybe we're never gonna see something, even if we decrease these error bars. Maybe it's not enough to really know what's going on. Let's have a look from a different perspective. And this is something nice that happened also here with Michele Moresco. I'm not sure if it's here, but he had this very nice idea to look around and ask people what are your methods to constrain cosmology, specifically these new probes that are coming up. And we were also asked to join in. So this CV here means cosmic voids, and tell him or tell each other what is our take on this. So we wanted to compare with each other. Are there any things that we can say about H naught or omega matter, sigma 8? So I'm not going to talk too much about H naught here, but we'll focus more on the clustering and matter density constraints. So okay, we were able to contribute here, but now I'm going to maybe more focus on what we mean with cosmic voids. So first of all, what do I mean with cosmic voids? What I was very surprised by, 2 weeks ago, I was in the Museum of Modern Arts in New York, visiting Alice Pisani. And I wasn't aware they also had a section on cosmic voids there. This is one of the pictures of those. But also this one was actually quite surprising because it really reminds me of some of the pictures that my PhD students did. So you know, this coloring of different voids, it really looks like that actually. Of course, you all know this one. Not sure this, but maybe you could also think about something like the void there. But then I was also surprised to find this written at the wall, which is kind of describing what voids are, a little bit of matter, maybe. But okay, jokes aside. Of course, what I'm talking about, if it's coming up, let's see, is the cosmic voids and the large scale structure. So what is our picture of that? We can run simulations and see how does the matter cluster in the universe. This has nicely been done by Tom Abel and his group in Stanford, and a very nice visualization shown here. The dark matter is the dark stuff. The bright yellow things are galaxies. And then there are the white regions where there's not much. This is what I'm gonna focus today on. So these are the cosmic voids. And as you can see, this is now evolving to low redshift. They are becoming more and more prominent and actually dominate the volume content of the universe at recent times. So this is our picture from simulations. And this is what we then start with when we want to define them. We take a density field. Let's say this is just a simulation. And then the idea is to apply something that's called the watershed transform. So we define a density. So we start at the minima and raise this density threshold. And by raising it, you will see that there will be ridges disappearing at some point. And this is when you realize, okay, this was a local basin that's separated by these ridges. And then you continue raising this and you will find more of these boundaries disappear. And this is how we actually build up a nested hierarchy of these depressions. And in the end, you can do this in simulations, you find these things. This has been implemented in Mark Naring's Zobov code already more than 10 years ago. And this is the technique that's now one of the kind of standard ways to do this. Here's a nice visualization again. These spikes show you density minima in 2D. You start raising the density. So it's like pouring water on this curved surface. And you find these disconnected regions, call it in different ways here. And in the end, you'll basically, you're space filling the whole domain with separate voids. And there's another question, of course, before we can do this, we even have to start with the density field. So how do we get that? We usually have galaxies or dark matter particles. We need a density field. We use various ways to estimate densities. One way I think is very neat. It's called Voronoi tessellation. So think of the US and their states as a tessellation of the area. And all these states have capitals, right? And they are somewhere, there's one capital in each state. Now, this is one possible tessellation of this. You can also do the United States of Voronoi, where all the capitals are now arranged in such a way that the states of the area, all these points in each state are closer to that capital than to any other. So it's a unique tessellation in the sense that it's assigning all points to the closest capital. And now we also have a very nice density estimate because we can now say the inverse of the area is something like that. And also it's good because we can now have arbitrary boundaries here, but this definition still works fine. Just ask what are the closest points to this capital. And that's very useful for us in astronomy because we know we live with all these funky features around our stations, so we have to do that. And then once we have the tessellation, here's an example in 2D again. We can look again for the density minima and see how far they extend out until the density decreases again. So that the cells get smaller and smaller, that means the density gets higher until at some point you find a ridge. So this is the smallest cell, and the neighbors of that cell will again start increasing. That means you find your neighboring voids, another void. And in the end, you get these structures in 3D simulations that look like this. They kind of make sense by eye because they stop at the boundaries, which look like filaments and sheet-like structures around expressions. Okay, and then we have complications in observation because we don't have these wonderful regular boxes with periodic boundaries, but we will have in Euclid, we will have these patches of the sky where we'll see something of the large-scale structure. And then we'll have the galaxy and the zodiacal light where we have foregrounds and we don't see a large-scale structure. And we will have, of course, a light cone. We don't observe everything at the same redshift. We will look at the past light cone. So there will be a varying density of tracers with redshift. And all of this we'll have to take into account. But as I said, the boundaries are already kind of nicely treated when we do this tessellation techniques. But of course, anything that intersects them, if any void that intersects with these boundaries, we'll have to throw away because we don't know what's going on behind. And this is all already implemented in this software package that some of you already of course use. I know this is called Bead for empty, and it implements the techniques that I just spoke about. And then this is what we can do. It's a work example, a BOSS survey, and Sophia made this wonderful plot where you can see now when we apply this to the light cone data and MOX, we can identify these regions just here highlighted with these circles. You can see there is some empty spaces. This is just because we have a mask that's applied to the data. We're not absorbing the full footprint. We have some holes, and of course, around the holes, we will have to throw away more objects. But we will have still a number of these candidates here that we can use to do some interesting science. So what can we do now? One of the ideas that has been around for a while is, let's think of voids as standard spheres. But what I've just shown you is that they don't really look like spheres, right? They're arbitrarily shaped, messy objects. But if we think of them as like averaged over many of them, we would expect them to be spherical symmetric because we expect our universe to be spherical symmetric. There's no preferred direction, cosmological principle. So let's think of an average void stack, and then we would expect it to be spherically symmetric. Here's the observer, the line of sight, plane of the sky direction. So what we observe is something like a center of the void and the galaxies around it that define it. And of course, we don't observe these distances. These distances depend on our assumption on cosmological model. So we will have to convert angles and redshift distances. But that depends on our cosmological model. So what we can do then is we assume a model, calculate these distances, we take distance ratios, and check whether this ratio is 1. That would say, okay, in this, if we chose the correct model, this would be 1. But then, if it's not 1, it means we found a geometric distortion. Right? So there's some non-spherical shape, and it means, okay, maybe we chose the wrong cosmology, and we have to iterate until we find it correct. And that's called the Euclid-Paczynski test. Been around since Euclid-Paczynski proposed it many decades ago. But the voids are actually quite suited to use this test. Of course, unfortunately, this pure picture of isotropy is not true because we also have redshift-based distortions, meaning galaxies have their peculiar motions on top of the Hubble flow. So the redshift that we get from them is not just a cosmological redshift, it also has Doppler shift. And that, if we just interpret it as a cosmological redshift, will displace them. And we will have to take this into account. Right? So galaxies typically, so Doppler shift mostly acts along the line of sight. And in the dense regions, we get the fingers of God. And in the empty regions, we get more like this pancake expansion. And we'll have to take this into account. So what happens now is we move from real space without any peculiar velocities to redshift space. We'll get another distortion here in red. It's called the redshift space distortion. So now the voids will on average not be spherical anymore. But luckily, we can find out what is the cause of this distortion because we can understand what causes them. What causes those distortions is simply the underlying matter distribution. The matter sources the peculiar velocities. Okay, so what we want to get is what's the ratio in redshift space, so S parallel over S perpendicular. And in order to get that, we assume essentially mass conservation, saying everything that streams out here must have come from somewhere. So mass is conserved. And you can actually do this just at the linear level. It's a continuity equation at the linear level. And you need to assume a growth rate of structure. The growth rates we know in large-scale structure is called F. So how does this look? This is the continuity equation. The peculiar velocity just depends on the enclosed density fluctuation and is proportional to the growth of structure and these other prefactors here. And the enclosed density fluctuation is just this integral over the density profile. But this is just linear perturbation theory. So you might wonder why would we bother? Because linear perturbation theory usually doesn't get us very far in cosmology. This has been done decades ago. But when you check in simulations, you can actually check, you can measure the density profiles, you measure the velocity profiles, and then you apply this equation to the density on the left, and then you see the lines, they actually reduce this very well. And most of the regimes of this, you can see these are now voids starting at around 9 up to 70 megaparsec in size. The largest ones are the ones that are not so compensated. They are more flat around here, but they have the highest outflows. Makes sense because the small ones have this compensation boundaries, a lot of matter around them. That means particles outside here actually see an overdensity. That means they will fall into this boundary. But within this voids, they are always outstreaming towards. Now you can see, okay, but there is maybe an indication of a breakdown of this linear theory. Okay, so let's say, okay, here it's these voids at let's say one void radius around these 10 to 15, maybe 20 megaparsec scales. This could be the breakdown of linear theory. You could interpret, that's what we kind of interpreted here. So we actually realized, and we wanted to see, is this now the breakdown? Is this the fundamental scale of linear theory? And recently then with Nico Schuster, the PhD student in our group, we checked in the magnetic simulation of Klaus Dolak. And this is okay. This is also very simple dark matter, all very ideal. We checked in the halo distributions of the hydro simulation as well. And now we went down to boxes of only 50 megaparsec and checked, for void sizes down to only like 1 to 2 megaparsec. And we see again the same thing. There seems to be maybe at some point starting to be deviations, but these deviations now happen at more like 2 megaparsec, not 20 megaparsec. So actually, I think we're now convinced that maybe there's no breakdown of linear theory inside voids at all. Maybe we can just go all the way, because we're always seeing the same structure, no matter how small the voids we look at. We're always seeing this, and now we're really happy to see that maybe we can push this to arbitrary scales. Of course, it's limited by the size of voids we can actually observe. It's not going to be this size. But it's encouraging to see that this linear dynamics is holding up even in these tiny ones. I'm not saying they are linear structures. You can see the density fluctuations are order 1. Okay, they're not linear structures, but the relation between density and velocity can be described as linear dynamics. Okay, and that's good news because now we can apply this simple formalism to the data. And we started with the BOSS data. Here you can see the void catalog. So this is northern, southern galactic hemispheres all the dots are void centers. And here are the number density of galaxies that we use as tracers and the voids extracted. See, of course, the number densities are much lower because voids are very large. But they follow roughly the structure because you can always identify more voids when we have more galaxies. See smaller voids. And then we applied this idea. So we stacked the voids in directions perpendicular and along the line of sight. So we'll actually get something very regularly shaped. This is now from the MOX where we tested it. So this is why it's basically noise free. But you can see also the model that we put in, which is basically just assuming linear continuity equation. The same data is on the right is just decomposed into the Legendre multipoles, monopole, quadrupole, hexadecapole. You know this from galaxy clustering. Most of you probably know. And the nice thing is you can see already the hexadecapole is essentially zero. So the data is mostly living in the two first multipoles here. And the model can describe it quite easily. So essentially the anisotropy here, this is the redshift space distortion, is fully described by the quadrupole. And this is how the data looks. It's more noisy, but it shows essentially the same features. If you go back and forth, you see it's very consistent. And it works quite well to reproduce most of these features. So what's next is, of course, Euclid. And that's what we're preparing now in the collaboration. We want to see how well can we do this with a new data set. So Euclid will have, what I showed you here are a couple of thousand voids that we can use. And Euclid will have hundreds of thousands, so factor 100 more. And yeah, it's gonna launch this summer. And now the redshift range is also very different. Well, BOSS was, you could see here, the mean redshift was 0.5. So the maximum was maybe 0.8 or something. Here we'll start at 0.9 to 1. It's really different regime. And this is now what we already started to do. We looked at simulation data we can check so far. So we don't have the real data, but we have the flagship mock, which is a light cone as well, within an octant on the sky. And here you can see the void centers that we extracted from that. You see it's already much denser, this plot, than the one I showed before. And here's the same number density plot. We have slightly higher densities of galaxies and, of course, the voids. Now we have the luxury to bin in redshift. Before it was harder to do with the BOSS data. We had maybe 2 redshift bins possible, but here we have now 4. And here's the raw void size function extract from that over all redshifts. So you can see we can get down to roughly 20 megaparsec in voids, up to almost 100. And here again, from a couple of thousand voids to 44,000 voids on the octant. But just to be reminded, this is just an octant. The footprint of Euclid will be roughly 3 times that size. So here's the measurement of the mock data in 4 redshift bins. It's very smooth. It almost looks like the patchy mocks before, but now this is what we expect from 1/3 of the Euclid final data. So it's really nice. The same in multipoles. You can see that the model deviations at the very low distance here are essentially just some noise that amplifies itself, but it doesn't matter so much because there's not so much constraining power in the very center. Most of the signal really comes from where the quadrupole peaks, which is slightly within the void radius. And so this is now the forecast for Euclid that we did. This is a compilation of the measurements we have so far with this technique. And it's essentially 2 things that we get out. We get the growth rate of structure measurements and the axis ratio, which is essentially just a ratio of distances, cosmological distance. So essentially it's the angular diameter distance times the Hubble as a function of redshift. And you can see all these measurements here are real measurements that have been performed already. And in this regime, we have the BOSS data constraints you can see here, which was already nice because we could show that this Alka-Kwaczynski test is really powerful. And if you really just compare this to BAO in terms of AP test only, it's a factor 4 better because we have much more tests. BAO lives at 100 megaparsec. We live here at around 30 megaparsec. So we have many more modes or volumes to sample. Right? So this is powerful already in BOSS, but in Euclid, we'll get the same thing in 4 redshift bins with twice the precision. And also, of course, in a redshift range where we haven't covered anything yet. Yeah.
So why is it only that redshift because smaller redshift?
Because that is the spectroscopic window that we have, because Euclid is going to use mission line galaxies mostly, this is the target area. There will be galaxies all the way down to redshift 0, but only photometry. And for that, we don't get good enough redshifts to get this resolution along the line of sight for distances. But there will be a possibility of maybe to also use those voids for other purposes like lensing. But this is a different story. Let's see if I get it. I also can say something about lensing, but probably you have to stop me at some point. I'm not sure about the time.
Do you have 100 slides?
50, so too many. But I can. This is the most important stuff, and later I can ask you what you're maybe more interested in. I can talk about it. So just to summarize the constraints that we forecast for Euclid, this shows you, like, lambda CDM on one very simple comparison, what you can do on, say, omega lambda or omega matter, same thing, just one minus the other. What Planck has, what BOSS voids could do already, and what Euclid voids are expected to be able to do. And then if you really compare just this, I mean, this is a single parameter, at this level for this test, you could even compete with the main probes of Euclid, just for statistical power. But of course, I'm not saying that here the main probes, they also constrain all the other parameters at the same time, which we're not. But this test is very powerful for constraining the background expansion. And if you're living in just in a lambda CDM boring universe, then you only have one field parameter, and that's of course then very well constrained for the background expansion. And H0 will not constrain. But then you can expand model space and look at dark energy models. And here we opened up just equation of state. And also that seems to be quite feasible, 10% constraints. Once we're starting to open up more like W0, WA, and so on, we're getting more degeneracies. It will be hard to pin this down just with the test alone. But of course, the idea then will be to also combine with other constraints and then again, handle this from different angles. Now, there's more, of course, Sophia is working on this. The void size function is another output that I haven't talked about. It's another data set that's constraining. So this one will be available from Euclid as well. And Sophia and Giovanni have explored this for Euclid, how this can be modeled, and how this will help us also constrain cosmology. So the idea is very similar to what people are familiar with, cluster mass function. So we'll get the density or the number of voids as a function of their size. So by the way, when I talk about radii, I always mean effective radii, which means you take the volume when you suppose if it would be in a sphere, that's the radius of that sphere. Of course, they are not spheres. And then just to jump to the conclusion, what do we get out of this? The interesting thing is that, again, direction and parameter space can be complementary to each other. And especially this one here has been now, I think, confirmed more and more times in many papers by Sophia and others, that sigma H omega M really looks into a different direction in space. Because this is what we're used to with most probes. Sigma 8 anti-correlated with omega matter, because you can either increase the matter density of the universe, make more heavy clusters, but to compensate that, you can also decrease the amplitude of fluctuations. But turns out for voids, it's not the same story. And now everybody always asks about this, which is it's the same, just confirmed with Quixote simulations, which is why I have this plot now, which we added to the paper, which is very nice to illustrate why there is this different in this direction. So just look at the linear power spectrum. And the key here is to look at the omega m dependence. So sigma 8 essentially, for voids or for clusters does the same thing. Increase your fluctuations amplitude, and you increase your abundance of massive clusters or large voids. Okay, but for omega matter, it's a little bit different because you can see there's actually a pivot scale here in the matter power spectrum, just linear matter power spectrum. And voids typically live at different scales in clusters, and they tend to, cross this pivot boundary to the left part, where now the response to omega matter is actually the opposite. So you can just translate this into the void size function, which is using extended projector theory essentially, or VDN model. And there you can see, okay, the voids will be going this way. So you increase omega matter, you decrease the large number of, that is the number of large voids. So it's the opposite to what happens to clusters, where most clusters live here, you increase the number of clusters. So the omega matter is a bit different, and that helps us to break degeneracies. Okay, and now I could also start a bit about lensing. Roughly how much time do I have here?
10 minutes.
Okay.
15 minutes.
I have lensing. I also have void clustering. Maybe I have to choose one of those. So the 2-point statistics of voids or the lensing around voids. I don't know. Is there any preference?
We like the voids.
Lensing. Let's continue with lensing. So yeah, I mean, of course, you can use them as what's called maybe anti-lenses. Okay, light is not converging around them, but more like avoiding them. And so when you flip this, maybe you've seen it, of course, you've seen this plot. I just flipped it around because now you can see that it, light rays kind of go around these empty spaces. And instead of these beautiful arcs around massive objects, you can see something like here, maybe, where now you get this, not tangential shear, but maybe radial shear, it's called. Right, so you get the opposite effect. Of course, you also get demagnified, but that's maybe, I don't know if that has been already measured or not. But of course, Georgia, most of you, she's been quite involved in the DES analysis, dark energy survey. So she actually constructed void catalogs from dark energy survey, which is now a bit different data set. Okay, we don't have spectra, we have photometric redshifts only, which limits our ability to actually 3D resolve the large structure so well along the line of sight. Nevertheless, we just thought, okay, let's see what we get. And this is what she got. Void size functions in DES from red magic and red mapper samples. So these are the attention algorithms of the galaxies and the clusters there, this is a mock for mocks. You can see what happens when you now switch from spectroscopic to photometric redshifts. Of course, there will be an effect. But surprisingly enough, for the clusters, you could see that the voids inside the clusters were not so much affected by this anymore, because first of all, the redshifts of the clusters are more accurate. You have multiple galaxy clusters, you have better redshift estimates. And secondly, they are sparser, so actually they trace out larger voids. And compared to the effective scaling of the smoothing of the redshift uncertainty, that's smaller compared to the size of voids. So actually, they were quite close to what we could get. Anyway, then we were looking into the tangential shear. So we actually used these voids and stacked tangential shear profiles around them. And we could see, yes, indeed, there's a negative shear, which means a negative surface excess mass density, or instead of excess, the opposite, right? And you also see a little of the compensation around them. You see there's also a model for it where we had a template to fit this. And then the nice thing is you can now compare this also to the projected 2D correlation function. And you see a very consistent answer. So it basically tells us that the light and the mass, which is controlled by the lensing, follow each other quite nicely. It also implies that essentially the bias, which enters in quadrature here, and only once here, is essentially scale independent on these steps. And then we can constrain, for example, since we have probed the mass with lensing, we can constrain the mass profile like we do with galaxy clusters. And this is a constraint that we can get from a template fit to this data. We can constrain some of these free parameters, which are phenomenological, and see how does this density profile actually look. It's very consistent with what we've seen before in simulations. The central density is not very well constrained, but here these boundaries are quite nice. So this is not yet at the level of really probing cosmological models, but it's interesting because it really gives you a handle on these regions very deep inside voids, where you also expect maybe other effects like neutrinos to be interesting, or non-standard dark matter models could kick in there.
That previous slide was cluster voids, voids defined by clusters.
Now, we actually use, again, the galaxy voids because they are much more numerous, more signal to noise. What will happen with them is they will tend to be aligned with the line of sight, elongated, because the ones that are not, they will be smeared out, so you have a selection effect. So yeah, that's why we don't have a full model to predict this thing. We're kind of modeling it more in a logical way. So we're not constraining cosmological models yet. If we wanted to do this, we would have to better, understand the selection effects and also to model the profile itself of those principles, which is also not something. And again, for Euclid, this is also an idea that we have, and Marco Bonici was leading this, to forecast what void lensing measurement could add into the constraining power. So he ran this in kind of a spherical harmonics analysis forecast, where you have the standard Euclid weak lensing constraints, the void lensing constraints, which are not strong. But then you can do the cross correlation between voids and lensing. And these are just void abundance, then void lensing. And that actually seems to really get you better constraints. Again, you're breaking degeneracies and helping constrain some of the parameters. And also here, including dark energy and neutrinos. Here, the improvement is not super huge, but here, some of them are very encouraging. All right, and then I have void clustering, but probably I'm getting to the end. 5 minutes. Okay, I can. Okay. So we can also think of voids as just traces of the logical structure. So far, I was only talking about individual voids and the structures inside them, stacked, whatever. But now, what if we look at the logical structure on larger scales? So this is like a projected slice of matter, galaxies in a simulation. But you could do the same with the void centers. You just, what's the number of voids in a given volume? And then, you get this. It's kind of looks like a noise on that, maybe. But we investigated this a bit more. And the idea is, let's think about this on the large scales. What can we probe on more large scales? Maybe the initial conditions, right? So CMB, of course, it probes very well. The large scale fluctuations, and they're very well constrained to be Gaussian random. But maybe there's room for deviations from that. Like there's anomalies, people are still looking for non-Gaussian features. There's a cold spot. So people look at that. And so the motivation also is to do this maybe with voids. And one of the simplest extensions of initial conditions is, let's expand this to a first order non-Gaussian field in a Taylor expansion, so you get FNL. And this has been already constrained quite strongly on. So it's at the level of 5 or smaller, meaning there's not much room. But anyway, any detection of this parameter that is order bigger than 10 to the minus 2 would be significant because it tells you there's something more than just a single standard single field inflation going on. Really. So the idea is basically use the cosmos as a collider, right? That's what Akani Hamed and people do, and tell us maybe something about really fundamental particle physics from very large scales. And in the void perspective, what you do is, okay, we measure power spectra, usually with galaxies or matter. So this is the matter power spectrum. This is then the galaxy power spectrum, biased version of the matter. But we can also measure the void power spectrum, which is, as the map suggested, basically white noise. Okay, there's not much to see here. Maybe it doesn't help us at all. But then there's also the option to do cross power spectra. Okay, before we do that, okay, I subtracted the shot noise here, and you see the bare power spectrum is very, very much below the noise. So it's very much here, and then it has this ringing features, quickly decays because of the void density profile. But we have the cross power spectra, okay? So we can measure not only the galaxy mass cross power spectrum in yellow, but also the void matter cross power spectrum. And it has a clear signal here. But that's something not observable because we don't see the matter. But we can also measure the void galaxy cross power spectrum, the green one. So this has a very similar feature, much less noise because it's a cross correlation. So the shot noise doesn't matter much. But this is something we could measure. And you can see this feature here is actually, this is a negative peak. I just took the absolute on the log scale here, but this is a negative dip because on void scales, galaxies and void centers are anti-correlated. Right? So it's negative power. And you can now look at the large scale bias of voids as well. So this is done for, again, a range of void sizes. And you realize the larger voids are actually starting to get negative biases. Why is that? Well, they're anti-correlated with the large scale structure. And then they have this dip, which corresponds to their own profile. So this is basically going inside the structures of voids here. But on the large scales, they look like linear traces of the matter density. And the nice thing is you can see that actually these negative bias voids are actually the ones that are undercompensated. So the ones that are not so, they have these smooth ridges. So they're actually the ones that are also expanding everywhere. And then if we switch on non-Gaussianity, this bias switches on this 1/k squared dependence, which is known quite a long time now from Damal et al. Was one of the first to point this out. So this is a nice signature because you can essentially just observe the scale dependence and conclude maybe on the amplitude of non-Gaussianity. This is nothing new, but now voids, what voids add to the picture is that since they can have negative biases, so you see the amplitude here goes with the linear Gaussian bias. This can switch to the negative regime. And also this delta C, which goes in here, which is critical density collapse, has to be exchanged with the negative threshold for voids. So again, get sign switches. So if you now start looking at voids of some size, you see there's actually a positive correction for negative FNL. And then you go to larger voids, and then you get the opposite again. So it's always nice to have, I think, these kind of effects will get different signs at different regimes because you can be more sure if you really want to measure something like this tiny FNL that there is something. Because this should be happening if you're going for this. If this is not happening, then it could be also systematic effect or something. And in this paper, we concluded that if you now include voids into the game with other tracers, you could possibly increase the sensitivity because of these features by maybe a factor of 2. Okay, but now I think I could say a few more words about neutrinos. Nico Schuster did something about this too with the Demnuni simulations. Why are neutrinos interesting? I said before they populate more strongly the insides of voids. They're not clustering so much at the boundaries. So there is something here to look for them. You could see the differences. Here it's still hard to see anything. So we try to use voids. And indeed, what you find, these are the central densities. When you switch on neutrinos, you get more shallow voids, less deep voids. Okay, that makes sense. But that's the case for dark matter. When you now look halos to trace voids, most of the effect goes away. It's more subtle to see. But then we can also look at, again, the linear bias voids, as I just introduced. And there, we were happy to see that maybe not only dark matter, but also halo voids, the ones defined in halos, seem to have some residual effect as a in their bias, large-scale bias values. This was an interesting observable, maybe, but this was just a very exploratory study where we didn't go deeper to see really how well it is. Okay, and then I'll just leave my conclusions by saying you have all these, nice things to do. You can use them as complementary probes, measure geometric distortions, dynamic distortions. I can also tell you actually something about tests of gravity, which I didn't cover, lensing and the clustering, maybe about neutrinos and inflation. And of course, the cool thing is that now we have all these things coming up, not only Euclid, there's more, and the numbers will just increase by 2 orders of magnitude. So that I think justifies why we live in the age of exploration for voids now, because we really have many things still to do which have not been done with them before. And if this still hasn't convinced you that they're interesting, I suggest you to search for cosmic voids on NASA, on the ADS, and look at the citation count. It's pretty interesting to see how well they have been receiving attention recently. But that's it. Thank you.
Welcome to Nico. We start with Federico.
Okay, I have 2 questions. Maybe I can ask 2 of them. If you can go back to the slide, the first slide in which you put a picture of a PhD student. So maybe
that was
16. So the one when you said that you find that actually one of the first, so that you find that the profiles are more linear with respect to what you maybe here. So here I didn't understand what is the reason. So here you found that it's quite linear. In the previous slide, no. I didn't understand the.
Sorry, I forgot to say why.
Why?
What we realized, why is this deviating? It's because you are sampling here, with very few particles. It's always the trouble with voids. How do you get? Why did I cut off? Actually, I cut off something. Yeah.
So you mean that the error bars is not representative of the
yeah. Because the error bars are based on jackknives. Like you will usually jackknife over many voids, but they are also biased here, these data points, because what do you do when you encounter a shell or a central shell with no particles? You can set the velocity to 0, but why? You could set it to 17.5, whatever. It's just when we set it to 0, we're biased to 0, so this all will go to 0, but it doesn't mean that it's non-linear or anything. It's just that you're not sampling the velocity.
Okay, thanks. So the second question, again related to the error bars, but at the end, clustering of voids. The error bars.
Do you have to go?
I
can do it here. I can do it here.
An exercise.
Yeah.
No, the one that you also did another picture of.
The power spectra, maybe?
No, the ones at the end on primordial non-Gaussianity.
This one.
This one. So the error bars here, I guess, is something related to simulations. I wonder. So if you have any idea of Euclid, which kind of error bar there is. So the relation between these error bars and what we expect with Euclid, or we can do something like this new.
Yeah, we haven't done the full exercise, and you see that the FNL is huge. This is of course ruled out.
Because there is no.
But of course the effect is huge.
There is no projects. There is no paper in the key project of Euclid related to clustering of points, or you plan.
No.
Because you think that this is even for Euclid better.
No, I mean, just nobody's really doing this, but. Could be a project maybe. I mean, there is one project on non-Gaussianity with the standard approach, right? Yeah. So I think that the point is that maybe voids alone will not be competitive with the standard approach in this respect, but maybe adding them in could help. Yeah. But we haven't pushed it all the way to.
So you didn't try with the production.
No, because we have not even put this on Lightcon data yet. This was all
for non-Gaussianity, just to see the expected error on the bias.
Yeah. True, and especially maybe it's interesting because the emission line galaxies have a bias not so different from one. They're not so biased. So for the standard approach, this amplitude could be quite low. But when you get voids, you can push this to negative values. Maybe you get some. Yeah. So we haven't investigated. Could be worth it.
Carlos, please.
So I wanted to ask about the slide of Newton Frank, the lens.
Yeah.
Exercise.
Oh, it's easy now. I can.
So, yeah, so particularly, so here you can use the model and project this in 2D and actually get the delta sigma of the voids profiles, right? Correct.
What do you mean that?
So you have this void profile, then you can integrate along the line of sight and get the tangential shear for a model, right? You can build up. And so I was wondering, when you get this signature of the profile, so in cluster outskirts, so we have some particular feature which is the secondary for region, which is people they call it spectrum, because it's much more appealing. But in this case, in the void, so why do you have this peak, which is above, which is at the slightly above the void radius? What is going on there? So is this also in voids? You can define a region of not secondary in full, but something going on.
It's the same. It's the same that we've seen already here.
It's the compression.
Yeah. So you see the feature here. This is just the boundary.
Okay, and how do you call this region? So what's going on to the galaxies at this region?
These are, because the way we define voids, we always, it's a watershed transfer. So we're actually going all the way to this peak until void is open. Meaning, you see that this is usually at one void radius. And it's just all the stuff that can be filaments, sheets.
But for the clusters, we have these flashback features, not theoretically.
Yeah.
So and I was wondering phenomenologically, what's going on in the voids?
Dynamically, you mean?
Yeah.
Yeah, I mean, sure. There have been papers already by Birchinger in the 80s that do this. They have these shell crossing regions, and then they have oscillations of particles around them. You get shocks if you have gas and stuff like this. Sure.
So that could be something interesting.
Yeah, but I'm not sure how you can actually, because you're averaging over large regions, how you can really see some. And when you actually look at, say, comparison between dark matter only and hydro, we do this also with Nico, the magnetic only. We try to find, what are the baronic effects? They're surprisingly small because you're averaging out. You think you're averaging a lot of stuff around here, so you're kind of getting rid of a lot of stuff. You see very, very small differences for very small voids, but otherwise it's very light.
Mauro, then I see Marco online.
Yes, again, on this plot, right? You were saying, so basically here, I don't know if I got it correctly, but you said that you were somehow, you wanted to verify that they follow the dynamical perturbation, follows the linear regime. But since, voids are on average under dense regions, and in the peak there, I see just small over densities. Shouldn't I expect them to be linear?
Linear, you would expect this linear relation, you say? Yeah. If you say so, maybe. But, linear, to me, it says order, when we talk about linear perturbations, it's much smaller than one. This is not much smaller than one here. I would say 0.01.
Negative, I have no idea. How does it work with negative?
Yeah, so if you actually go,
it's close to 1 in absolute value.
-1,
Okay.
basically zero density is very nonlinear.
Very nonlinear.
Okay.
And if you do perturbation theory more, I've seen papers that did this already a long time ago. They actually get very nonlinear value. Every perturbation order you go, you get positive and negative correction. It's a nightmare. Like theoretically, it seems to be a nightmare.
So in the negative regime, close to -1 is supposed to be nonlinear.
Yeah.
And then why you verify that it's
so yeah, I mean, I'm not saying this is all the, so I'm not saying I'm modeling this profile with a linear model. Okay. I'm just measuring the density here, and I'm plugging it into the linear continuity equation to get the velocity. So what's linear is just the relation between the density and the velocity. What's not linear is the density fluctuation itself. It's not linear, okay, technically. So I also am not sure. I mean, people did this. There was Hiranya Paris recently with a student that took they what they call anti-halos. So they invert the initial conditions where they find halos in the final conditions. They tag the particles, look where they are in the initial conditions, then they switch the sign of the initial condition and see where these particles go in the other simulation. So they are going into voids, expanding. But then they do some Zeldovich approximation, actually can kind of get similar profiles just using Zeldovich, which is also linear. So maybe even that is not super nonlinear, but yeah. And the other reason, maybe you can also think of this regimes that are below the mean density of the universe as, you know, universes with low omega matter, and also universes with low omega matter evolve less nonlinear as ones with high omega matter.
Okay. I see Marco Baldi online. Please, Marco. If you are speaking, you are mute. Marco. Marco. No,
we have to
so
increase
It should be somebody
nobody
who's
yet.
tested it before. Marco, can you hear us?
Can you write your question on chat, maybe? If you listen me, I hope so, because it's not.
Yes.
FNL.
Yeah. Questions about FNL.
Can imagine. It's working on simulation. No.
Yeah, so what are the prospects to get FNL down to more realistic values? And also
Test is also only for local.
yeah.
So the problem is local.
yeah. So good question, of course. Realistic FNL, we haven't tested it, but in principle, the forecast you can do it with. And if I do show, if you believe this kind of behavior, and we tested this with these kind of separate universe approach, where you actually generate such a correction with different, having different boundary conditions, different initial parameters. When you believe this, you can always make a forecast, even if your simulations have a larger FNL. I don't now remember exactly what was our constraint or forecast on the accuracy on FNL, but of course, it always depends on the simulation volume that we used, and that was like not fixed or matched to any any observations that we get. So it was really just the first kind of step in this direction. And also for other types of non-Gaussianity, we didn't check. But since you get this 1/k² dependence for FNL local and much less, maybe 1/k or not even anything for these other types, of course you won't get these effects. But of course, we haven't explored other things. You could now start opening up bispectrum with voids, maybe, say galaxy void triangle. These are all things that can be done. So these are all projects you could start, but I haven't looked into this. I hope
can you hear me now?
Yeah.
Yes.
Okay, sorry, my microphone was not working properly. Yeah, so thank you for the clarification. We started looking at non-Gaussian simulations with Sophia some time ago, but with somewhat smaller values. So in between 40 and plus or minus 40 and plus and minus 100. Actually, we didn't get any strong signal. So my question was really whether there could be any strategy to try to be more sensitive using voids to these smaller and more realistic values of FNL. But you answered already, so thank you very much, and sorry for not being there in person.
Okay, I will ask Sophia about the details about this.
Okay. So
Thanks.
in principle, you could use clusters just to amplify the value of B, but it's difficult to define a good number of voids using the cluster distribution. Because if you increase B, so you can increase the signal,
but you can also, voids open up the window to negative B. So what you actually want in a study, what sometimes called multi-tracer analysis of this, is you want a large spread in these bias values, because then you actually have a much higher signal to noise on this FNL. Because I mean, intuitively it makes sense, because now you're probing a regime where you get a positive correction, and another regime where you get a negative correction. And taken together, you have a much bigger, angle or a lever on this. So this gives you a better signal to noise.
I have a question myself, if I can just to finish, maybe, if you have no more questions. So what is, your opinion, the role of the algorithm that you are using to detect the voice? Because everyone is using bit.
No,
okay, there is also resolver. Okay, we know.
Okay, that's the same anyway. But there are also other
So, but what is the importance of the algorithm in this kind of perspective for void cosmology?
Yeah, I cannot give a general answer because it will depend on all the different applications, I think. If you want to maximize your lensing signal in the central part, if you want to get to the very lowest densities, maybe you want to look for just spheres with a minimal central density or something like this. It depends on what you want to maximize, and I think for my favorite application, which is this one, what we want to make sure is that we can model this accurately. So we want to make sure that this linear velocity relation holds. And there are indications maybe that in some cases it doesn't work so well, although also the spherical void finders have been tested and they also seem to get that very well. We also want to make sure that we get nice boundaries, because that's what we really get constraints our shape. If we don't get these boundaries, so often you have void finders that stop already at the mean density or even the somewhere inside the void, then you will kind of wash out the outer parts more, smooth that out. So maybe that's not as optimal anymore to find a shape which we want for AP patterns. But in the end, I think it's you just use whatever you like and test your pipeline. It's not gonna. I mean, it depends. Void size function, of course, will be much more sensitive to the void definition than this, because this is just a test of isotropy. You can do this with clusters. The trouble will be to model the whole thing, right? But you could do the same thing. It's just an AP test. So the point is that you can model it here. But yeah.
Okay, I don't see any other questions. Okay, we stop here. We thank again Nico. No worries.
Worry. Bye, everybody.
Now,